Hello, my name is Raymond. I'm an English student in the S6 class at the European School of Munich, and today I'm going to talk a bit about electric fields for the physics course at the European School. I'm going to briefly present some of the more qualitative concepts or general ideas, then talk a bit more specifically about the two main topics and the differences. Of course, also the formulas and calculations for uniform fields and for radial fields, and then finish up with a summary and some example questions. So, to some of the qualitative ideas. So, when talking about electric fields, we use a vector called the electric field strength, or sometimes referred to as the potential gradient. And since it's the electric field strength, E, we have a capital E for this. Please note that this electric field strength isn't the same as energy, and to denote that they aren't the same mathematically, we try to remember to write the vector sign whenever we write the electric field strength, since energy is a scalar and doesn't have the vector sign. Now about electric fields, so you have two different types of electric fields. You have a radial field, shown here, or you have a uniform field, as shown here. So for the radial field, the way to think about it is that if you have, for example, a charge, let's say in this case we have an electron, which is negative, it creates around itself a field which we can represent with lines. So if it's a single particle, like an electron, it creates a radial field that shoots outwards in all radial directions, which we represent with these arrows. And now if there were to be a proton in the vicinity, this proton would feel a force that would attract it towards the electron. That proton would also generate a field around each other, and they would in fact both attract each other and both move. We also have what's called a uniform field, shown here, which, since I imagine you just studied capacitors before electric fields, is a bit like a capacitor if you imagine two plates that are charged oppositely. So one plate has a positive charge represented here, and one plate has a negative charge represented here. And as such, this generates a uniform electric field, and note the importance of uniform, which means that it has an equal strength anywhere within the field, whether you're very close to the positive plate or very close to the negative plate. Theoretically speaking, it's uniform. Of course, pragmatically, this isn't necessarily 100% correct. As far as I understand, if you're within 10% of either side, you do get some variance and it doesn't stay uniform. But for the theory's sake and for our calculations later, this uniform field represents perfect equality in the sense that the electric field strength at any given point here in the field is the same. So if you were to place, for example, a proton or an electron into this field, so between the two plates, it would then feel an attraction to the opposite. So if you put a proton in, it would be pulled towards the negative side, and if you put an electron in, it would be pulled towards the positive side. So please note, we generally draw the electric field lines in such a way that they go from positive to negative. As you can see here, when we're referring to the direction of the field lines, we always draw away from the positive, so to speak, to the negative. Another importance of electric fields, or their representation with lines, is that the density of the lines represents the strength of the field. So the denser the lines, the more lines for a certain area, the stronger the fields. But for most of your exam, you won't really be drawing these electric field lines. It's simply for a qualitative representation and understanding. And who knows, it might pop up as a question. Also important is this idea of an equipotential, which is certainly possible with a radial field, but it's a bit more complicated, and I don't think it will feature or be of any importance for your exam. So let's just focus on it in a uniform field. If you were to place, for example, a proton or electron into this uniform field, then it would feel the force, and there would be an energy change, so to speak, if it were to move towards either plate. But if you were to move it simply up or down, so along, like along this green arrow, there wouldn't be any energy change. And the reason for this lies in the fact that along this arrow, the potential, or the voltage, so to speak, stays the same. And only as you move along the field lines do you in fact change the voltage. More to this later. So after a bit of qualitative analysis, we of course come to the more quantitative component. So as with most components of physics, you have a concept, and this is backed up with a few key equations out of which you can practically make all the other equations. So here it's up to you. As a student myself, I prefer to just remember the 2 or 3 key equations for each topic, and then in the exam basically derive the other equations from these 2 or 3 simple equations. So the real important equation for electric fields that is universally applicable is F equals QE. So what does this tell us? It tells us that the force that a element feels in an electric field is its charge times the electric field strength. And this makes sense. So the stronger the field is, then your proton will feel a stronger force. Makes sense. The more charge your proton has, or the more charge your electron has, the more force it will feel. Also note that since the electric field strength is a vector, our force is also a vector. This equation works out. And if you wish, you can practice your dimensional analysis to in fact check that this equation works out. But this is really the key equation that you can derive so many of the later equations with. So moving on to uniform field calculation. So this might all look like a lot at once, but let's just start off with this image. So if we go back to our idea of these 2 plates opposite of each other, a bit like with a capacitor, with positive charges on one and negative charges on the other, with this electric field between them, then we of course also have a voltage difference, as we did with a capacitor. And this voltage difference is then the potential that you could measure on the capacitor. Now, we also have a certain distance between the plates, and we have the electric field strength that is uniform between the 2 plates. So we have these 3 components, and we want to somehow combine them into an equation that we can use only for uniform fields. So the way we do this is we go back to our roots of electricity and circuits with a common formula that energy, or delta energy, is equal to the charge times the voltage. From there, what we also know from hopefully mechanics and also in general is that energy is the negative of work, and work is force times distance, or maybe if you've gone into a bit of calculus already, the integral of force for distance. Then if we grab back to our key equation, which is F equals QE, shouldn't be a minus there, my bad, wait, I'll just quickly delete that. Shouldn't be a minus, so F equals QE. And we put this equation, F equals QE, into the earlier equation with the energy. We get that the change in energy is Q times E times delta X, and of course the minus is here now because energy is negative work. And now with Q times E times X, we can simplify it once again with the earlier equation. Since we know that energy is Q times V, we know that V is energy divided by Q. And if we take this and apply it to this energy here and divide by Q, and we do this of course on the other side too, we get the simplified and applicable equation delta voltage is equal to minus energy times a distance. And of course you can rearrange this as you please to answer any question about the uniform field. But do remember that this equation here is only applicable to uniform fields, not to any other type of electric field. So now moving on to radial field calculation, we have the second key equation. Since uniform field calculation is generally quite simple, most questions that you'll probably encounter, they'll be worth a lot of points in your exam, will be radial field questions, and as such I would recommend this as the second key equation to remember. It's commonly referred to as Coulomb's law, and it's truly important, and a good way to remember it, I find, is that this component here is just a constant, and if you want to, when you're writing the equation to try and remember it, you can refer to it as k, but of course at some point you're going to have to remember that it's 1 over 4 pi epsilon naught times q1 q2 divided by r squared. And a good way to remember it is if you compare it to the Newton's law of gravity. So we know that for Newton's law of gravity, the force is equal to the gravitational constant g times the two masses divided by the distance between them. And you can already see there's a very big similarity. You have the constant, you have the two charges, you have the distance between them. Here you have the constant, the two masses, and the distance between them. So it's very similar. So if you know Newton's law, then it shouldn't be too hard to learn Coulomb's law. Briefly to the constant, if you're interested, the reason for the 4 pi is if you link it with the r squared, you get 4 pi r squared, which, surprise, surprise, is the surface area, which is very useful in this case for our calculation, and epsilon naught, the electrical permeability of air, of course, is also important since most of this will be happening in air. So this is a mathematical equation. So if we now look at what it's describing exactly, we have two charges, q1 and q2, and they're a certain distance r apart. And then depending on whether the charge is positive, positive, or positive and negative, or negative and negative, or negative and positive, they will feel a force that either pulls them together or pushes them apart. And this force is dependent on q1, r, q2, and this constant here, which the constant doesn't change, so the true parameters, the distance, and the two charges. And now, as you've probably learned already, or you know, positive and positive repel, negative and negative repel, whereas positive and negative attract each other. And here, another important note to take is that the force that they feel is always the same. So if you remember back to Newton's third law, which is that every force must have an opposite and same reactionary force, so it has to be of the same magnitude. And as such, they're either both pulled at each other with the same force or both repelled with the same force. Exactly. So now moving on from this, using this, we are now able to calculate the force that any charge would feel based off of the electric field of another charge. And of course, they're influencing each other, which is why later we'll have to use some calculus to work out the energy, but more to that later. So simple questions might just ask you to apply this one formula, Coulomb's law, to find the force between two charges, but some deeper questions might ask you to find the electric field strength at a point which is generated by one charge. So the question, what it probably will be describing, is a situation as shown here. So you have a charge shown here of Q, and then it's generating an electric field around it radially, as we saw earlier in our qualitative description. And then a certain distance r from it, we want to know at this location x, what is the electric field. So to do this, we refer back to Coulomb's law, which is our gem. We then also refer to the number one key equation, and from this we can derive that the electric field strength is basically Coulomb's law, just taking away the second charge. So one way that I try to remember this, as you can see here, the electric field strength is just basically the same as Coulomb's law, just with one charge and not two charges. And the way that I try to remember this is that you pretend to have an imaginary charge, shown here, at the given location where you want to know the electric field strength. And this is the charge Q2 in Coulomb's law. What you then do is you apply our number one equation to reduce this force over here to just the electric field strength, and you do this by dividing by Q2, this charge, And this, of course, also then has to happen on the other side, because you have to treat both sides of the equation equally. And as such, this then cancels out, so up, up. And then you end up with the electric field strength being the same as Coulomb's law, but just with one charge, and that charge is the one that's generating the field. And of course, the distance from which you're measuring it. So the next possible question is a question about energy, or rather potential energy. So one important qualitative idea to note here that I'm sure you've already encountered once is that you decide where the potential energy is zero. So potential energy, you could say, it's kind of the physicists' derpy way of trying to not have a problem with the law of conservation of energy, because it doesn't really exist. I mean, the energy goes somewhere and then it comes back, but it's never physically manifested. So in that sense, the potential energy, you could say, be 100 joules, where someone else might say it's 50 joules. And the reason for this is that both of you are not wrong, you just have set the potential energy to be zero at different locations. So that's an important thing to note. You have to decide. It's similar to with gravitational potential energy. If you decide the gravitational potential energy to be zero at the ceiling, then any objects in the room will have a negative gravitational potential energy because they're below the ceiling. Whereas if your friend sets a gravitational potential energy to be zero at the floor, then all of the objects in the room will likely have a positive gravitational potential energy. So here it's just important to note that it is entirely dependent on where you decide to make the potential energy equal to zero. So this is a more interesting, advanced part that we have to do in this segment of the course, is that some basic calculus to determine what the energy is. So we know that the energy is force times distance, since we know energy is the same or very similar to work, and work is force times distance. Now what we used to be able to do was just simply multiply the force times the distance. If I just draw a quick graph of force times distance, we used to be able to just multiply them to get this area here, which was the energy. Well, the problem that we have now is that it's not just staying constant. The force is changing as we change the distance. And the reason for this is if we go to Coulomb's law, we see that the force is dependent on r. So it's dependent on the distance between the charges, and as such, we can't just multiply them, because as we change the distance, we also change the force. So we can't just multiply the force by the distance. Instead, we have to do some basic calculus. In fact, we have to do an integration, which is summing up an infinitesimal small distance infinitely many times to find what the sum area underneath our graph is. So to find the energy in this case. So we're basically integrating Coulomb's law over a distance. And since you're not required to derive this formula, this one might also be one you have to remember, but it's quite simple to remember because basically everything that the integration does is it can only affect the distance, since that's the parameter that's being integrated. So everything else is still the same. So the constant at the front, 1 over 4 pi epsilon 0, stays the same. Q1, Q2 stay the same. The only difference is that it's not r squared anymore, like in Coulomb's law, but now only in r. And the reason for this is that integration is the opposite of derivatives. And you probably have gone a bit into derivatives, which is basically lowering the power by 1. And what we're doing here is we're increasing the power by 1. And since the r is on the bottom, in Coulomb's law it's r to the minus 2, and it's turned into r to the minus 1. But this isn't too important. As long as you remember this formula for the energy, you're a-okay, and you don't need to know about the calculus or the derivation. Now the last point for a radial field is being able to determine the voltage. So to do this, we have to refer to our recently derived formula, or remember it, depending. recently derived or remembered formula. And we then have to go back to our roots of electricity to E equals QV. And if we rearrange that, we of course get V equals E divided by Q. And as such, we can then apply this formula to the energy one to find that if we divide both sides of the equation by Q, so do this to both sides, we can on the left side get the voltage, which is what we want, and on the right side we simply have to take away one of the charges, and we end up with this equation shown here. So if we now then apply this mathematical equation to a diagram, what we have is we have a charge Q, as seen here, that is generating this electric field around it, seen here, and then basically a certain distance away, R, at a point we want to know what the voltage is, and then we apply this equation. So the Q in the formula is the charge that is generating the field, of which you want to know the voltage at a given point that is a distance R away from the charge that's generating the field. So if you remember all of those equations, you should be fine. So I've tried to summarize it as well as I can now. So these are really the equations you need to know. If you go into the exam with these equations, you should be entirely okay. Of course, I've not included all of the equations I discussed here. I've only included the ones you need to be able to derive the other equations. So the most important that you really need to know is F equals QE. It's a fundamental to all of the other equations, and it's applicable anywhere. So it's the most useful one, so to say. Then you have delta V equals E times D, which is a good way of earning simple points, but do note that it's only applicable to the uniform field. Then we have Coulomb's law, which is the force formula for a radial field, very similar to Newton's law of gravity. So if you have some experience with that, it's a good way to remember it. But this is also really a killer that you need to know, and a good way to rack some free points. Then we have the electricity equation that you should already know, E equals Q times V. Do note this is only applicable to basically all of the circuitry you've met so far, except for capacitors. For capacitors, it's E equals a half QV, but I won't explain that right now. And then the last equation that you should know, and that I think is easier to know and harder to derive, is basically the equation for energy, which is the same as that for force, simply not an R squared here at the bottom. Instead, it's just 1R. So keeping all of this in mind, I thought we'd go through 2 examples and then call it a day. So I've taken these from Mr. O'Dowd's sheets. I don't know, maybe if you're watching this, you'll have the same sheets. If not, then it doesn't really matter. These are just some of the examples that we had to do. Yeah. So this is question 7. It reads, 2 parallel metal plates are affixed 20 millimeters apart and are maintained at a potential difference of 1000 volts. So with questions, it's always the best idea to draw a diagram. So if we draw a diagram, we have 2 metal plates. I'm very bad at drawing. You want to label the diagram. You want to draw it bigger than what I've drawn, because you can really never draw the diagram too big. So you have the 2 metal plates are 20 millimeters apart, and the potential difference, let's do this in a different color, delta V is 1000 volt. So basically, when you're reading this, you should have a few things clicking in your mind. So the first one being the 2 parallel metal plates. So this sounds very much like it's generating a uniform magnetic field. And hopefully, having learnt off the equations, you should know that for a uniform magnetic field, we can use the equation delta V is equal to E times delta X. So on your answer, you should write this equation at the beginning. It's also good for practice to do this. Even if you think you know the equation, it helps you remember it, and it's just good form, to be honest. Then we look at the question, we see it's asking for the potential gradient, and we know that the potential gradient is another word for the electric field strength. And now if you write down, this is also a good idea, on the right column, all of the parameters that we know. So we know that delta V is 1000 volt. We know that the distance between them, D, is 20 millimeters. And we're looking for the electric field strength. And we know that we can use this equation because it's a uniform field. So then as such, we're able to, see, okay, we have delta V, we have D, or we can also refer to it as delta X. And we're looking for E. So this equation is perfect, and if we rearrange it slightly, we see that delta V divided by delta X is equal to E, or the electric field strength. And then if we put our values in, so we put in 1000 volt and 20 millimeters, we get 1000 divided by, please note, this delta X is in standard units, so in meters, so we have to rearrange the 20 millimeters to be 20 times 10 to the minus 3 is equal to the electric field strength. And then with a calculator, or I'll give it a shot just like this, so 1000 divided by 20 is 50, and then flip the 10 to the minus 3, so it's 5 times 10 to the 4. And then for the electric field, the unit, you can have, there's two units. You can have Newton per Coulomb, which is from F divided by Q, or you can have, as I'm going to use now, what I think is easier, but it's completely personal preference, you can have ohm per meter. So as we just did delta V, not ohm per meter, sorry, volt per meter. And then this is our answer. That was part A. I hope you could follow it. Now I'll quickly erase this to do part B. As you can see, I'm not very good at erasing this software. Oh, no, didn't want to do that. Okay, I guess we'll just have to deal with a bit of this extra because I'm scared of erasing the question. Okay, so the second component of the question asks us what force would act on a particle in the gap. I shouldn't have erased the picture, so I have to draw it again. Charge carrying 2 times 10 to the minus 11 coulomb when its distance from the negative plate is 10 millimeters or 2 millimeters. So I'm going to draw this a bit bigger this time, as I told myself to do last time. And I'll draw in the field lines this time just to make it a bit easier. Yes. So if we say that this is a negative plate, it doesn't really matter. And we say that this is a positive plate, we have kind of two line points. So this is when it's 2 millimeters, and this is when it's 10 millimeters. Okay, this is massively unproportional since the whole thing is 20 millimeters, but okay. And we know from our other question part that E is, I believe, 5 times 10 to the 4 volt per meter. And then as such, we also know from our qualitative knowledge that since it's a uniform field, it doesn't actually matter where our charge is as long as it's inside the field. So whether it's 2 millimeters from the negative plate or 10 millimeters from the negative plate, it doesn't matter whatsoever since we have a uniform field. So it's a bit of a trick question here, and the answer is in fact the same to both parts. So I and 2I have the same answer. Now to finding that answer, we have to use our key equation F equals QE. And quite simply, we insert the electric field strength from the first question, and from the part B, we are given what Q is. It's 2 times 10 to the minus 11 coulomb. And if we put those into the calculation and work it out, then we'll get a value for the force. And sometimes you might think that this value is terribly small, but we're talking about tiny, tiny particles with very little charges, in this case 10 to the minus 11, and thus of course very small mass also. So here we would have a force of 10 to the minus 6, I believe, and as such you could write it, if you wanted to, as 1 micronewton. Exactly. So this is an example of a uniform question. And then for a radial sphere, for a radial question, so here question 15, a small sphere bearing a charge of 1 nanocoulomb is situated at a distance of 180 millimeters from another small sphere carrying a charge of 4 nanocoulombs. Calculate the work that must be done in moving the first sphere to a point 60 millimeters from the second. And then what is the electrical force with which one sphere acts on the other in the latter position? So it's a two-component question. So we have a small sphere, a very bad sphere, and it's 180 millimeters, from another small sphere. With small sphere, they mean a point, which is important for Coulomb's law since it only works for points. And these were given the charges of, so here we have Q1 and Q2. This is seeming awfully familiar, I hope. Plus 1 nanocoulomb, plus 4 nanocoulombs. Exactly. And then, and as we can see, it's important to know that they're both positive, so they themselves want to repel each other, but we want to bring them together. So we basically have to use our energy formula. So you either remember this or you can derive it from Coulomb's law itself again. But we know that the potential energy that the charges will gain is equal to 1 over 4 pi epsilon naught, the constant, times Q1, Q2, divided by R. Then we know that we've moved the first sphere to a point 60 millimeters from the second.